So, let's get going here. There's much ado, of course. Oh, and one more thing, of course, that I've forgotten to do. Let's see, escape. I'm pretty sure. Oh no, we're good. All this is going out over the air, so people are going to be like, "What is up with all this weird nothing? I'm not even going to watch this crap." Anyway. So this is the memory Hotplug on Android session. Hey Kate, Barrow's actually taking notes, so if you have other places to be or things to do. So yeah, memory Hotplug on Android. So this is a topic that has actually been near and dear to my heart for about 2 years. Ever since I started working with system MMUs at Qualcomm before I came to Lenaro. So I'll cast this problem in the following way. All these offload engines that sit out on the bus, on these SoCs, are kind of brain dead when they access memory. Now you're a hardware engineer and you're thinking, well, the easiest way for me to deal with life is to just build my machine so that when I need memory, I just access it linearly, which is okay. But when you get to cameras and graphics and these things, these buffers become really, really big. An HDMI camera buffering allocation is like 48 megs in the usual case. So to get around, to deal with this fact, and to deal with the fact that you don't want the camera to not launch, right? Because that would be bad. People are like, oh, I want to take a picture of my kid. Oh, no more memory, because Angry Birds is taking it all. Or the memory is fragmented. In order to deal with this, what people have done, system SoC engineers have done, is they basically just allocate this memory at boot. It used to be PMEM in Android did this. It basically alloc boot mem a whole bunch of stuff. Now, from work at Samsung and Lenaro, we have the continuous memory allocation subsystem, which is a cleaner way to do this at boot up. And that allows you to essentially reserve a large amount of memory at boot and keep it around forever so that you can satisfy these allocations. And the camera will come up immediately. Well, there's two problems with this. One, that memory is always powered up. So, and that's a significant chunk of memory. Two, that memory is not available to the rest of the system. And so, back in olden days, when you had the G1 coming out, which had 256 megs of RAM, a significant portion of that 256 megs was actually reserved for the offload engines. If you could come up with a way to actually deal with this so that system memory could use, or the system could use this memory, and then there was some mechanism that when you needed the camera or you needed these things that had higher priority, that those would actually get the memory, then you could ship less RAM. You could save power and ultimately provide a better experience because you could, for example, support more apps could run, etc. So we're not as memory constrained in some regards, but in other regards, we're exactly where we were. Because now we've got big old HD resolutions. And so really, the problem is still there. We have more RAM, but we need bigger buffers. So anyhow, I've thought about this for quite some time, and this is kind of the result of that thinking. So there's a tool in the, or there's a feature in the Linux kernel called Memory Hotplug. And Memory Hotplug is built for servers. It's built for servers to essentially online and offline NUMA nodes. And that's cool, right? Adding memory, deleting memory. And it takes this idea that I can try really, really hard for a long time to get memory. So if it takes me 10 minutes to free up a segment of memory because I need to swap out a NUMA node or something like that, then that's fine. I'll just keep working on it. It's a data center. It's huge. It's a big server. So anyway, I'm kind of jumping ahead in my slides. Excuse me. But memory hotplug essentially gives you two features. It allows you to logically unplug memory, so basically move everything out of memory where the memory is still actually resident in the machine, and it allows you to physically pop memory off and pop memory on, so physical hotplug. So, server memory hotplug. Change the amount of memory and install and remove DIMMs or NUMA nodes. Mobile memory hotplug. So, okay, this is cool. We want to use the stuff that's in the Linux kernel, and we want to apply it to mobile. So in a mobile sense, you're not popping DIMMs. I mean, you could. And the first person that actually desolders a RAM with the memory hotplug, I mean, maybe that would take you 10 minutes. So you could say, okay, memory hotplug, I'm going to desolder this RAM, and I'll solder on a new one. But that's probably not going to happen. So you use logical memory hotplug. And you're using logical memory hotplug in the effort of you want to get everything out of this RAM so that you can power it down effectively and save some power. So to do that, you essentially, it's all user space driven, and this is just for this is just how you would go about offlining, logical offlining of this memory segment. So memory hotplug breaks memory all up into segments, and the idea is that I tell a segment, okay, I want to offline you, and then what's going to happen is its migration's going to kick in, and it's going to try to migrate out all the pages and drop all the page caches in that segment. So migrate all the movable pages and drop all the page cache. So it can take minutes, and in the current implementation of memory hotplug, it can fail. So before I move on, this is actually a big problem because you don't want to take minutes to offline memory. In a mobile case, you want it to offline, okay, maybe you have 300 milliseconds, which is a long time in an SoC. But you want it to go offline, and you want to guarantee that it'll go offline. And then you want to guarantee that it can come back online. So I didn't know anything about this until Andrea Gallo, who used to be at STE and now is the Lenaro Enterprise lead, pointed out to me that STE has actually been doing a bunch of work here. And then it was pointed out to me that Intel is doing a bunch of work here, and I'm sure NVIDIA is doing a bunch of work here as well. And Qualcomm did a bunch of work here. So everybody's kind of doing this thing. And they're able to do it because RAMs now have these cool features. So the RAM guys didn't want to be left out of the whole power management game. They said, we can do stuff too. And so they had temperature-compensated self-refresh, or they have three features in most modern-day RAMs. Temperature-compensated self-refresh, partial array self-refresh, and deep power down. Now, temperature-compensated self-refresh is automatic. So it turns out that if you live in Alaska or Siberia or anywhere it's cold, you're actually saving more power. Because when it's cold, the DRAMs don't have to be refreshed as quickly. They'll save more power. But if you're in Hong Kong in the summer or in Texas in the summer, your battery is going to last probably 20% less. And there's a cool little feature on the chip. It's got a little temperature sensor, and it'll actually adjust the refresh duty cycle to compensate for the temperature. Really cool stuff. Well, the guys also put on, and by guys I mean guys and gals, the guys and gals also put on a feature called partial array self-refresh and deep power down. Now, what this can do is it can say, given your DRAM configuration, I can actually power down part of the RAM. And I don't know if you remember everybody probably had a computer organization class in college where you actually sketched out, okay, here's the RAM array, and this is how the things are laid out, and I can configure it X, Y, Z. Anyway, I tried to do all that for this presentation, but I was like, we're just going to call, I can power down 64 megs. I bring this up because in a mobile case, as Andrea pointed out to me, your memory is actually interleaved. It's not only soldered to the board, but it's interleaved. So you have to deal with the fact that it's interleaved and power down the right bits to make sure that you're actually powering down a contiguous chunk of memory and you're not powering down 16 bits of, your 32-bit memory access, or I'm sure once 64 bits comes on, powering down the top 2 bytes or top 4 bytes as opposed to the bottom 4 bytes. So anyway, you got to get it all configured. And anyway, the fortunate thing is that STE and Maxim, right? Maxim have actually worked this all out, and they have all this really cool, all the code's actually there to do this feature. So that's awesome. Now, before I talk about Maxim's adventures in upstreaming, I want to talk about, does this actually matter? So there's some swags out there. Approximations, right? We're engineers. We approximate stuff. So the approximations set this number at 5%. 5% power savings across the board. Now, this is assuming that your phone, when it's running, is using up about a watt. If you're watching a movie or surfing the web, you're about a watt. And that's pretty consistent, actually. Even as you're moving up and moving down in processes, I mean, it all kind of scales, right? I might move down in process, but I may have a bigger screen. I'm doing more things. So this is actually kind of consistent. And out of that watt, the calculations, I'd say probably conservative calculations, put the amount of power savings at runtime at 50 milliwatts. So that's 5%. That's big. We spend a whole bunch of time. Oh, so this is a comment to Tim Bird. So at ABS, we had this, is Android the new embedded system? And Tim Bird said, well, I can't ship Android on 32 megs. And I said, oh, well, maybe you could if you didn't have to give a bunch of memory over to all of these camera buffers, right? These big buffers. At boot, you could actually do it at runtime, and you could save a chunk of memory. Now, I don't know if you can get down into the 32 megs, but one of the big reasons why Android had to start out with lots of memory was just this issue, this needing to reserve memory at boot. So I think, well, if you alleviate that, well, I can ship less memory. Now, to just put this in perspective, yes?
Is that using both the self-refresh and the power down?
Yeah. So it's basically like you're doing self-refresh or partial array self-refresh 50% of the time. You're doing deep power down 20% of the time. And you're doing temperature-compensated 30% of the time on the balance. So that's essentially, and that calculation is actually all laid out in the references I've listed at the end, how they did that. So if you're curious. Now, this calculation is totally a guess. But I wanted to kind of gauge, like, all right, so Lenaro spends a lot of time doing big little. But when you really look at a phone, what is the real big power hog? It's huge power hog. It's the screen, 70%, right? So any kind of power management you do is in that 30%. That's it. The CPU is... That's not the problem. But, any little bit helps. So I'm going to say that if you use big little will probably come out to about 15% power savings at the end of the day. Assuming that the A9s use 150 milliwatts, assuming that the A7 uses 150 milliwatts, where the A9s are using 300 milliwatts, which is a third of the watt during runtime, assuming all that, well, that's 15%. So this is a big deal. 5% is nothing to sneeze at. And as Michael Hope always told me, it's a game of inches in power management. Okay, so this is all well and good. We have this cool feature. Let's integrate it into a system. Now, we're SoC people. And SoC people are not Mel Gorman. and they have no idea how really the VM works. And so they take a very simplified approach, and they say, okay, well, I'm going to do what I've always done, and I'm just going to carve out a chunk of memory, and then I'm going to write a hook to a governor. That's essentially going to say, okay, well, if not camera on suspend, or actually during runtime, if not camera, then power this thing down. That's essentially what it's going to look like. And then if camera, power it up. That's, of course, assuming that the contents are not important. Now, this is the same bit of code that Lenaro has been trying to make better forever, right? This is what we do. But users start here. So how can we actually take the Linux approach and integrate this more deeply into the VM so that, A, it's not ARM specific, right? So I'm not, and by ARM specific, I should actually say it's not device specific. And it's something that everybody's going to be able to take advantage of. So Maxim actually sent a patch set that had the first bit, had all this support, had the partial array self-refresh support in it, and had the integration into the VM. And it hooked into the buddy allocator, and it was, so Mel Gorman kind of came back and was like, well, this is cool, but how about we do it this other way? And this other way is essentially uses CMA and a balloon driver. So what are we trying to do here? What are we trying to do? We're trying to, at runtime, identify a large contiguous chunk of memory that we can power down. And we're all VM-ish people, so we know that it's extremely hard to get a large contiguous chunk of memory at runtime. So Mel's idea is, okay, let's use a balloon driver to actually, with a continuous memory allocation backend, to actually blow up a contiguous chunk of memory. So I'll take you through the more detailed idea. So at boot, you actually reserve a CMA for the partial array self-refresh. And this CMA is going to be on the order of 64 megs. That's what the STE buffers were. So at runtime, there's no CMA allocations. Now, there's something, after reading through the code, I don't actually see how this works, but I've got a couple of questions out there to see if this is actually possible. So just bear with me. There's no CMA allocations, which means that Linux is free to actually use this entire chunk of memory. Now, the question I have is actually looking at the CMA code, when it actually does the region, when it actually reserves the region, it's just building up a data structure. That's it. But it does actually go through the page. Well, so that's my question, is it actually goes through, it builds up a data structure and it says, okay, well, all these pages are part of the CMA. But then how does that actually get taken out of the VM, and how does that interact with all this? So I think that what happens is that Linux is free to put movable and page cache pages into this CMA when it's not being used, which is kind of the big deal. I believe that's the case, which means it works. Yeah, go ahead.
So the devices probably want non-cacheable memory, but Linux, when it's using it, it's going to want cacheable memory. So how big is the memory type?
That is a great question. Also have no idea. We're really at the higher level, like conceptually, you know. Yeah, but I know exactly what you're talking about. But there is, so the only thing I can tell you is that SMMUs make this better. So I'm going to use that escape valve whenever you ask me those questions. Ard.
So you mentioned about the PASR that it has this interleave and this granularity.
Right.
That applies to DPD as well?
It applies to DPD. Now the question with DPD is how, I think with DPD, it's actually the entire RAM. But I think that's vendor specific, and you got to read the data sheet. And I didn't do I didn't look into that, but it's definitely something I want to look into to see.
For the DPD, at bank level.
What's that?
For the DPD, it's at bank level. You have several banks in each file.
Yeah.
So don't you have to go by chip select? No.
No, that's the cool thing, is it'll actually do intra chip select with the partial array self refresh.
Oh, yeah, but for the deep power down.
Oh, for deep power down, yeah, I think it's based on chip select. Because why else? It's a different thing. So yeah, go ahead.
Because the self-refresh preserves the content, right?
Right.
So you don't need to do as much probably if the self-refresh is the only thing that is. Well,
Yeah, that's a good point. Yeah, maybe you're taking it out of self refresh. So maybe what it is deep power down is actually just a deeper power state along the same alignment, and the partial array self refresh is actually a less power state. So
Yeah, because you keep PSA, you keep some logic running, up and running compared to GPD. That's why.
yeah, and that makes a lot of sense.
There,
Yeah,
you save much more with GPD.
right. Okay, that makes a lot of sense.
The other thing is DPD is a feature of the LPDDR.
Uh-huh.
It doesn't apply to DDR3.
It doesn't apply to DDR3.
I don't believe so.
Oh, okay.
Maybe someone else here has more information, but I don't think it applies to LPDDR3.
That's something to look at.
So if it is LPDDR2, I mean, all these Hotplug techniques are far more compelling than DDR3, which consumes more power and has low cost.
Yeah, fair enough. Fair enough. Okay, so the idea is you declare a CMA, and at runtime you have no CMA allocations. Now, what's happening here is you're not actually using the camera at this point, and you're running full out. So the next step, on idle, you can read that as on idle or on need to launch a application that needs this. So in this case, what happens is you blow the balloon up. And you will drop page cache and migrate out anything from the region that you need to achieve this balloon. So you have now an upper bound on actually completing the camera allocation, which you didn't have before, which is the whole point. I may not get there a lot. Well, so there's one. Well, you don't have an upper bound yet. Sorry. You're migrating out, right? You keep trying. But let's say your memory is just let's say memory is just not behaving, and you just can't migrate enough, or you're oversubscribed, which is the other thing, right? Which is the real issue. You're oversubscribed, so you have nowhere to migrate to. So your pages in your CMA region are stuck. So how do you get them out? My absolute favorite feature of all time, the Android low memory killer. Not OOM, but the actual Android low memory killer. So what it does, right, is it ranks processes. So I can actually blow the balloon up and rely on the low memory killer to essentially help me out here. And if I go through and I actually get through the entire system, I might have to kill every single app to actually get my camera to launch. But at least I know I can do it. Now, I think there's a corner case in there about, okay, well, when system server starts up, where is it located? And there's probably some other things. But this would say, okay, well, if I can kill all the apps, then I have enough memory to do what I've got to do. So maybe maybe as a first cut, right, you could say, okay, well, when I do this feature, I'm going to change the Android low memory killer to essentially just nuke all the user apps. And it's a low-priced Android phone, so who's going to know the difference, right? Because that's where you're saving the memory, or why you're saving it. Okay. So then when on wake up, or when I actually stop using the camera app, then I can deflate the balloon. And the system can now run 16 instances of Angry Birds. Of course, it doesn't do that, but I can run Angry Birds and Facebook and blah, blah, blah. So that's the idea. So a couple of issues with this. And I'm sorry, I thought this was going to be more of a like two-way thing, but I guess I just wanted to talk to you guys about stuff.
Just explain it too well.
Yeah, well, it helps, right? So some issues. Quality of service. So that's why we're doing this in the first place. That's why the Android low memory killer kicks in. That's kind of the key thing of, I think, why this really hasn't come up. Latency, so what is the upper bound on killing all the apps? Can you guarantee it in 300 milliseconds, which is probably okay? I break out the 300 milliseconds because if you can do anything in 60 milliseconds or less, and the user isn't going to see it, that's kind of underneath the threshold of the user actually seeing it. And people are kind of used to apps taking a longer time to launch. And then kind of what I consider this, that this whole thing is bringing up this kind of hand of God VM tactic. It's this idea that the current kind of regime of 4KB pages is kind of old, man. I mean, we're getting to the point where we do not kind of need to think about re-architecting, I think, how the VM works in general. And I think one thing that we could do is, assuming SMMUs become fairly prevalent, you can actually get to a place where you could say, okay, well, I want to have a two-level general paging scheme. And you kind of see that right now with transparent huge pages, where this two-level thing is kind of getting into the kernel now. So the reason I bring all this up is, right, the ability to get a huge chunk of contiguous memory helps you out in more than just an offload engine. When you're doing an SMMU, in fact, you have to have large mappings. If you don't have large mappings, you won't actually be able to keep up. You won't be able to run at speed because you'll spend all your time faulting. And there's actually some good analysis that says with an SMMU, like, you can't even use 4KB pages. You won't keep up at all. So the idea is, okay, well, other things are going to want this ability to be able to quickly and efficiently handle large chunks of contiguous memory. And so maybe if Linux actually expands, maybe if we can get this kind of two-level page handling more widely used, widely integrated into the kernel, then maybe all of these use cases become easier and we don't have to do these hacks like the low memory killer coming in and essentially clearing out the space. Things become easier, et cetera. So anyway, memory management unit. So these are cool. Like I said, remember I said hardware manufacturers like to, or people that implement these offload engines like to look at memory as linear memory. So what the SoC hardware engineers did was they said, well, we've heard that OSs keep things in pages. So we want to get in on that action. So what they do is they stick an MMU in front of that engine. And that allows the engine to see memory contiguous, and it allows basically the engine to see a contiguous memory block virtually that may be physically discontiguous. But there's all sorts of issues with that. I mean, it's huge. It actually brings up this huge issue, which is distributed memory management, which is really cool, actually. It means that Linux is no longer, it brings up the question, does Linux have to be the boss of the VM? Does Linux have to be the boss of the tables, right? If you've got other components actually doing memory management, how does that all work together? And if you really look at the kernel and you look at things like DMA buff and you look at all these buffers, the higher level problems are really these problems with distributed memory management in general. So yeah, I mean, and SMMUs, they'll become more and more prevalent, and you'll see them on more and more SoCs. And it's a classic, like the hardware guys are, this is a cool feature, and then you got to work it out in software and how you're going to do it. Okay, so I can tell people are kind of getting antsy. So the first RFC came out. The second RFC is in progress. It hasn't hit the list yet. This 3 is a great presentation, much better than mine, that shows a full breakdown of all this. So that's the docs. That's it. That's the idea. Any other questions, comments, concerns? Yes, sir. Yeah, no, there are stupid questions, but yeah.
Why do you need CMA? Because you don't need physically continuous memory, apart from performance.
Yes, that's a great idea, or that's a great point. I don't know that you need CMA.
Well, but that SMMU will not be for every single device in the system.
Okay, so just say for one device with SMMU.
But remember it's a good question, but it's actually a different problem, right? That's like a why do we need CMA session, whereas this is like, okay, how do we hook PASR into the kernel?
Yes,
Right.
If you need the system MMU to fix, go back to my earlier question.
Yeah.
The system MMU to fix the cacheability problem.
Right.
There's no cacheability problem because you don't need CMA.
Right. Yeah. I totally appreciate that. Yeah, and I honestly haven't done a lot of thinking about that particular thing. I do know that one of the speaking of your cacheability problem, it's actually a worse problem than that. Like that's just a particular attribute, right? One of the big problems with all these drivers is that people don't just want to do cacheability. They want to diddle with inner shareable, outer shareable, all those wonderful ARM VM isms that you have to hook up to. So, and the VM doesn't even have support for 20% of what you need in that regard. Because you are really, I mean, to get a graphics driver to work, you're really getting in there and doing analysis of okay, who's touching what but yeah, so anyway, I don't know really where I was going with that except to just, yeah, I mean, I think that there's, it deserves a good think.
What is the status of, has this already been implemented on some phone?
Hang on one second.
Okay, for the section that you're going to offline,
Yeah.
you may want to mark that section as only memory that can be moved.
Well, so that's what I believe that the CMA, so when you when you create the CMA, that's what the CMA is doing. That's essentially what it is, right? It's saying you can put movable or page cache into these pages. You cannot put anything that is, it's not, right. You can't put kernel mem in here. And so yes, that's exactly why you use the CMA in the first place. It's just a means to an ends. But anyway, did you have a follow-on point to that?
Okay, so that was the question then. So in the moment that you're trying to offline it, if there's any non-movable pages that you just can't, right?
So that's a good point. So one of the ideas I had originally was, well, why don't I just not do migration at all? Why don't I create yet another way to tell memory that you can only put page cache here, and that's it. But then you get into the whole like mapping region and the way that, whether these buffers are in user space or kernel space, and I kind of just lose my mind at that point. What's that, John? Yeah, page cache may get dirty. So then you have to say, well, then you have to go John's volatile ranges place, and then he gets all grumpy because he's like, I haven't gotten volatile ranges up, and I'm mad about it. But then you get, so everybody just tell John, you're doing a great job. Just keep going, man. But yeah, all those are interesting things. Yeah, honestly, I'd like to introduce that into the VM, that it would say like, it's just the volatile range thing, man. I don't flush these, don't do anything. I just need memory. Do decode. I don't care if it goes away. Yeah, go ahead.
Okay, last question.
No, please.
What have you thought about this when you decide to use that, you may have a device that can only access that memory window. Now, while your one device is active, you use it for kernel data.
Yeah.
Kernel data, and I don't know, you don't know what that device is.
Yeah, so that's interesting, and I think that I haven't really thought about it, but it's a good point. Like, what are the security implications of doing things like this? I actually think it kind of helps security in one sense. If you could actually say to the kernel, I want a bunch of pages that I don't care about, I just need memory, then you could do something like, if you're in a compromised security situation, right, you can just nuke all that stuff immediately, right? Zero latency. Because the latency all comes from the fact that it's either dirty or there's something in there you want to keep. So if you can make that distinction, of course, what's really going to happen is it's all going to go into trust zone, and anything you were curious about security, I think all goes into trust zone.
Well, what I've seen from some security, like GPG and so on, when they need secure memory to store like a key or something, they use M-advice to make it non-movable. So it goes into the non-movable area. And it goes out of this scope.
Right, non-movable. Thank you, Linus. Yeah, so go ahead, Vish. I'm sorry, I preempted your...
What is the status on this? Has it already been implemented? What is the?
It's already been implemented, and Maxim says that he has his implementation works, but is a little bit has some stability issues. So he's working through those before he posts them. But yeah.
Latency is not that great.
Well, so what? All those issues and the governors and all that stuff hasn't really been worked out. This is what's been done is, how do I, in a architecture independent manner, handle PASR and DPD? That's all that's been done. But in terms of how do I track the latencies of DPD, offlining, and all that stuff, well, there's tons of projects for all that stuff. Okay. Well, everybody's looking at me and not looking at their laptops, which I really do appreciate. I know I've been guilty of that at time to time in some of your guys' presentations, so I apologize for that. But anyway, this is it. This is the last session. So before we all go away, does anybody have anything else?
Thank you, Zach.
Thanks, Kareem. Thanks, everybody.